The Hubble telescope has revolutionized the observation of space. If the satellite masses 11,110 kg and orbits at 552 kilometers, how much force does Earth pull on it? Well, once again, I've given you a distance, but I've given it to you in the wrong units. So you have a distance and you have 552 kilometers, but I know that every 1 kilometer is 1,000 meters, and I'm pretty sure if I do the math, I get 552,000 meters. The mass of Hubble, it tells me, is 11,110 kilograms, which is the units that I wanted in, but I also need to know the mass of Earth. And here's the well, it's not a problem, it just means I need to go back to my grid and say that, okay, Earth masses 5,973 times 10 to the 24th kilograms. Okay, that's the information I need. I know that G equals 6.673 times 10 to the negative 11th, and I'm looking for a force again due to gravity, and that's going to be in newtons. Mass 1 times mass 2 over distance squared. So the force due to gravity, I'm going to replace G with this number, times 10 to the negative 11, times the quantity. So I take the mass of the Hubble telescope, and I'm going to multiply it by the mass of Earth, 973 times 10 to the 22nd. And all of that is going to go over the distance, 552, 000, and going to square it. So force due to gravity, and I'm going to leave this alone for a little bit while I solve the both the top and the bottom of the parenthesis. The top of the parenthesis, I got 6.63603 times 10 to the 29, all of that over 3.047 times 10, whoops, 04 times 10 to the 11th. Force due to gravity equals 6.673 times 10 to the negative 11 times the quantity 2.177852276 times 10 to the 18. So the force due to gravity equals 1.4532280824 times 10 to the 8. newtons. So if I were to respond in phase class, I'd go 1.45 times 10 to the 8 Newton, or 1.45 E 8 newtons.